There we go. Welcome to United Astronomy Clubs of New Jersey. So while I'm waiting for a couple people here to file down, because we are on site in Jenny Jump State Park at the observatory, it is rather foggy, cloudy, and slightly drizzly today. Uh, so while we're waiting for those people to file down, I do invite you guys to check us out on our website, uacnj.org. That's where you're going to find a list of all our member clubs, our upcoming talks, as well as talks we have had in the past. And it's going to tell you all about our club and how you can support our nonprofit organization. Uh, you can also check us out on our socials, our Facebook, Instagram, and Twitter. Uh, on Facebook, we do post what talks are coming up, and a couple of our members write various articles for local papers that are very interesting and intriguing to check out. That being said, sorry, I'm on allergy meds, and sometimes the puts you in a bit of a brain fog. So for the people here, we are using our headlights when we leave because we do not like getting run over. If you need the bathroom, it is the porta potty behind the lecture seating area. And also feel free to check out our little museum and gift shop area after the presentation. During the presentation, I'll be monitoring online because we do live stream this on Twitch and YouTube. So do hit those like and subscribe and follow buttons so you can get notified when we next go live. With that, our talk tonight is Anatomy of a Star with Paul Fischer. Paul has a Bachelor's of Engineering in Chemical Engineering from Stevens Institute of Technology and has worked in the environmental and chemical industries. Although always interested in celestial objects, Paul's official start in amateur astronomy was one night several years ago lying in awkward positions on his roof, freezing in the cold, holding a pair of binoculars. Since he caught a brief glimpse of the Galilean moons of Jupiter, he's hooked and has since grown and continued in the hobby and is currently actually our president here at United Astronomy Clubs of New Jersey and volunteers elsewhere. And with that, Paul.
Hello, everybody, and welcome to UACNJ. Thank you, Kim, very much for that introduction. And give me a brief moment here while I switch over to my presentation for the evening. Oops. Here we go. And I want to start this from, here we go, slideshow, from the beginning. That's a good place to start. And there we go. The Anatomy of a Star. As Kim said, I'm a member up here, volunteer up here at UACNJ. I'm also a member of NWJAA. We are up here a club of clubs. So if you are interested in joining us up here at UACNJ, did I get that right? Yes, UACNJ, as an observer, it would be great if you could join one of our member clubs also. Look on our website for more information on how to do that. All right. Let's go. Before we begin, let's talk about who's responsible for this presentation. And I'm going to say that I'm going to take down here in the bottom credit for any mistake you see in the presentation. I will take full responsibility for those. But a lot of the information I got and that I'm reporting to you comes from both a book I read by Kenneth Lang, The Life and Death of Stars, and also a lot of information from Alex Filipenko, Understanding the Universe, An Introduction to an Astronomy, which is a video course from the great courses. I recommend both highly. What are we going to go over tonight? Well, first we're going to introduce a particular star, then give you the inside scoop, so to speak, of that star. Then we'll talk about an origin story. Then we will maybe look inside the star and see what makes it tick. Then how does our chosen star compare to others? We'll talk a little bit about that. And then finally, we started at the beginning, we'll end at the end, and we'll talk a little bit about what happens to stars at the end of their life. And now we're going to introduce the sun like it needs a big introduction, right? It doesn't need a big introduction as far as we're concerned. However, note I put a subtitle of sort of because it's not really the sun. And I'm going to explain that a little bit. Why isn't it our knowledge of stars not just the sun? Before we go into exactly why, it's sort of, we do get asked, so I just want to clarify for everybody, yes, our sun is a star, and other stars would be considered the suns of their own planetary systems. However, we must be of two minds on this subject. First of all, when compared with data from and measurements of other stars, our sun is really kind of just average, an average star. It's unremarkable, but that's the scientific data, all right? To us, however, our sun is emotionally, historically, geologically, evolutionary, and physically indispensable. So for us, it's the most important star in the sky, right? So you have to have two minds of it. You have to have the purely analytical point of view, but the historical and emotional connection we have to our own star. We wouldn't be here without the sun. To us, it's the most important star in the universe. All right, and a little bit more, why is it not the sun specifically that we're speaking about tonight? And I did a little alliteration here. Astronomies are actually actuaries. The sun has been around for 4.6 billion years. Humans have been around for 200,000. We have not witnessed the sun in its entire existence. Therefore, we cannot speak of it in a historical context. We do not have the capability of stepping in a time machine in reality and going back 4.6 billion years ago to understand the full history of our sun. However, when looking at stars, astronomers not only have to take into the account the speed of light and the expansion of the universe, but also their statistical variation. In other words, it's not a bug, it's a feature. So when we look back or look into the universe, look into our own galaxy, look into other galaxies, we are actually looking at the statistical variation of all the stars and gaining an understanding of all the stars, including our sun. It works both ways. The sun has a very significant logistical advantages, right? We can't currently, and probably it will be difficult throughout the entire existence of humans, but we can't just go to another star and visit where it might be in its life as easily as we can visit our own sun and take measurements and understand it detailed how it is right now. So we are combining those two knowledges. We are combining the logistical convenience of our sun with our actuarial knowledge of the stars and the rest of the universe to come up with a sun or star model, and that model is what we're going to be talking about too. So it's our sun, but only sort of. We're understanding more about it than just its convenience to us currently. Our particular, and that's what I summarized in the last bullet point there. Our particular star is actually a very sun-like model. It's maybe not a stretch to consider it an every star. Here's the point where is it all going to be text? No, we're going to have pictures too. And so let's start here. The Solar and Heliospheric Observatory, SOHO, that's going to be our first picture. You do, if you're going to search, take the shortcut and search for it in Google, if you just put SOHO in there, you're going to get a lot of pictures of a neighborhood in New York City and no pictures of NASA, so you have to include NASA in your search criteria keywords also. That's the website right there. And the second picture I'm going to show you is current as of today. And this HMI is the category of the SOHO Observatory has a bunch of instruments on it. You want HMI. It's what you can see with a standard white solar filter. So if you have that beta film or another white film that on your telescope, or in whatever you're looking at the sun through, then this is the picture you'll see. So this one is actually 2 years ago, and you can see these numbers here with these little dots. Those are all sunspots, so interesting. But I want to show you the difference because we talk a little bit about the solar cycle coming up. That's today. So a lot more active right now. And it's we haven't even reached the peak of the solar cycle yet. So a lot more activity on the sun than even 2 years ago. Now those are just 2 days, but if you look at it long enough, you can see the solar activity has picked up for a number of days in a row. You can see the solar activity has picked up significantly over the past couple of years. Let's talk about why these sunspots start being generated, and what does it look like in the sun. First of all, let's talk about what are the materials of construction. When someone put the sun together, what did they make it out of? Well, let's hydrogen, 71.54%. The hydrogen is over 70% of what the sun's made of. Helium is another 27%. That leaves a very little amount of other material that the sun is made out of. So it's mostly hydrogen and helium. And so it is so the rest of the materials in the sun is so small that the astronomers just choose to put everything together in one category called metals. Right? Everything else that you can think of is a metal to an astronomer, and that's 1.43. Metals isn't a really satisfying answer, is it? Because that is everything else. So what does that look like? Well, here's the sun spectrum. And you can see that these lines, these absorption lines, these are actually dimmer and more prominent lines. Can actually tell you, these lines will actually tell you they correspond, these lines, to electrons in various orbitals in the various elements outer layer, and they will absorb and then re-emit light. The re-emission of that light happens in a random direction. It doesn't happen directly at us, so they appear as dimmer lines in the spectrum that we're seeing from the sun. And that's how we can tell that these other materials are in the sun. And right here is a graph, which I'm not going to bore you with the details. That's why it's small, so don't worry about reading it, except you can see here, up here is helium on this one, and hydrogen at this one, the highest content, as we said. This is the sun's, and then it takes a nosedive down here for the next 2 or 3 elements, and then it goes back up to here, up higher, and this is a logarithmic scale. So it's interesting. We have helium and hydrogen where we expect it to be the highest in the sun. Then for some reason a nosedive, and then this tapering production of elements, and then it eventually comes down at the higher atomic number levels, comes back down to where it took the nosedive originally. So what's going on there? Good question. So I'm answering my own. Hydrogen and helium, of course, came from the Big Bang. They're the most abundant elements in the universe. These guys come from non-stellar processes. In other words, you might have heard that we make a lot of our elements in the stars of the universe. These guys, that synthesis doesn't happen in stars. That synthesis happens through cosmic radiation bombarding other elements. So that's why they are occur infrequently in the universe and in the stars. Then these guys up here, before it goes back down again, are created in stars. And then these guys again are created in non-stellar means, cosmic radiation, but also it could be other cataclysmic events in the universe. So that's why, again, helium and hydrogen, the big ones, a interesting dip, and then some stellar creation of elements, and then again the dip. All right, so let's play a thought experiment for judging some things about the sun. First of all, the core temperature is in degrees Kelvin. That's an absolute temperature scale. So what might be in a meaningful temperature here on Earth for Kelvin? Let's call it 273 degrees Kelvin, and 273 degrees Kelvin would be 0 degrees Celsius, so it's freezing here on Earth. So 1.56 times 10 to the 7th is a little bit hotter than 0 degrees, than 273 degrees Kelvin. Let's talk about core pressure in atmospheres. So what is the pressure here on the surface of the Earth in atmospheres? Yep, 1. So here we are at 1.97 times 10 to the 11th. It's a little bit more pressure in the center of the sun. The mass in kilograms of the sun, so a car would be, say, a metric ton, or a truck, something in between those two. The mass of the sun is 1.98 times 10 to the 30. That's 1.98 followed by 30 zeros, so that's a big number. The diameter is in kilometers is 1.4 million kilometers. Its distance from us is 1.496 times 10 to the 8th kilometers, or about in miles. You guys know this. 93 million miles. 93 million miles away. That's I put this on 3 times, so I'm going to give this same information to you in 2 other units. That's 1 AU, 1 astronomical unit. That's how the astronomical unit's defined. And then that is also 0.0000. Let me make sure I got that right. It's 4 zeros. 0.000016 light years away from the Earth. The energy output of the sun in watts is 3.828 times 10 to the 26th. Again, that's that's about 4, followed by 26 zeros in watts. And your light bulb, before we had LEDs, etc., you might a very bright light bulb might be 100 watts, right? So what does that mean? Let's think of that last one a little bit more. And we talked about the sun being 93 million miles away. Yet you can walk out during a warm day and feel the light, the radiation coming off of the sun on your face. Think about a campfire. A campfire, if you get within say 10 feet, 15 feet of a campfire, and then walk out of its zone about by 1 foot, it gets cold all of a sudden, right? Now think of the sun. You're 93 million miles away, but you can feel it, just like you can feel a campfire 15 feet away from you. That's incredibly powerful if you're 93 million miles away from it and you can still feel it. So brass tacks, what's in the sun, really? The sun's an incredibly hot, incredibly massive object under gargantuan pressures. It's not made up of matter as we would normally experience it here on Earth. It is made of a fourth state of matter called plasma. What is plasma? Plasma is mostly made up of, at least in the sun, plasma is made up of hydrogen nuclei, which are protons, helium nuclei, which are alpha particles, and free electrons. So those atoms are completely disassociated. The electrons and the nucleus have been completely separated. Plasma is a fluid, even if it is extremely dense at the core of the sun. And how dense? What is the average density of the sun? This is a very interesting number here: 1.41 grams per cubic centimeter. That's the average density of the sun. What's the density that's near 1.41 of a very common substance we find here on Earth? Water. Water's 1. So 1.41 grams per centimeter, that's the average density of the sun. However, the core, where all the pressure and the heat and everything is, at the core, it is greater than 10 times the density of lead. And where's my point there? I lost my point, but so that's interesting. It goes from the entirety of the sun has the average density of barely above water to more than 10 times the density of lead. So an interesting variation there as far as density goes. So let's go over some of the features inside a sun. We have a convective zone in a star our size. We have also have a significant radiative zone and a core. So the core there, the next zone, the radiative zone, which is rather large in our sun, a sun our size, and then a convective zone above that. We have the photosphere on the outside, the chromosphere over that, the corona over that. And here are some features that you can see from the sun. You can see sunspots on the sun with an H-alpha filter. You can see prominences and flares, and that's it. So just remember these three parts here: the core, the radiative zone, and the convective zone. Those are the insides. Now, how do we know that interior structure? That the interior structure of the sun is revealed by helioseismology. It is it's similar to how geologists use earthquakes or artificially created earthquakes, use seismology to know what's in the below us in the earth. Uh, Low frequency, powerful waves traveling through the earth is how seismology is done. We can generate them ourselves here, but we also use naturally occurring earthquakes to do it here. Well, the sun has quakes itself, and the astronomers who are expert at this stuff can track those waves through the, see how they propagate and bend through the sun and make educated guesses about what's in, scientifically valid or rigorous educated guesses about what's inside the sun. The sun's also, besides those interior structures, the exterior and around the sun is its magnetic field. It's a magnetic dynamo, and this is where we get into the solar cycle a little bit. At solar minimum, let's call it, the lines are a little straighter. They go from pole to pole, similar, but not really, because the sun has always been very dynamic. Similar to how you'd imagine the Earth poles are. However, the sun has a differential rotation. The sun spins faster at the equator than it does at the poles. So it starts yanking those magnetic lines in a loop pattern. So as the solar cycle progresses, the magnetic field gets yanked, as you see in this picture here. You can see, say, the equator here is moving this way much faster, and it starts yanking the magnetic field in the direction of rotation. And then finally, the equator, since it's moving faster, moves far enough, say, away from where this whole thing started from here, that the magnetic lines start looping, breaking apart, and behaving rather erratically, and that would be our solar maximum. Then the equator comes around again, and in an 11-year cycle, it comes back to our solar minimum phase. So that's why that differential rotation, the equator rotating faster than the poles, is what causes the solar cycles. The solar cycle is 11 years long. It goes from solar minimum to maximum and back again. So you have to remember that the solar cycle doesn't mean from minimum to maximum. That's half the cycle. The other half of it is going from minimum to maximum, and then maximum back to minimum. That's the full cycle. It was originally discovered by recording the frequency of sunspot activity, which in antiquity they were doing this. So we had knowledge about this a long time ago. Flares, sunspots, CMEs, coronal holes, and other solar surface phenomenon that you've heard about, I'm sure, in the media, and atmospheric atmosphere phenomenon, they all vary with the solar cycle. It's important to study and predict the solar events and the space weather to protect our own, here on Earth, infrastructure, including satellites, astronauts. Oh, and I said infrastructure. I meant stuff like electrical grids and other things that are, terrestrial based. So that's a brief overview of our star. Let's talk about how they come into existence. So please be very quiet for the next few slides. We don't want to wake the babies. Does anyone recognize this object that's a stellar nursery? This is the Great Orion Nebula. This is the Lagoon Nebula. They are both stellar nurseries. That's where stars are born. These types of places. Just so you know, these are protoplanetary disks. We've seen some of these recently in the media, etc. This is in here. You can't even see it, but in here is the star, and these are actually the planets forming around the star. What is a stellar nursery? So we saw those pretty pictures. What did we look at? A stellar nursery is a cold, dense, massive nebula, a cloud of molecular hydrogen. Cold means in the stellar nursery case about 10 degrees above absolute zero, so 10 degrees K. Massive means a cloud that is tens of light years across. If you remember our AAU unit, the distance from the sun to Earth is 0.0000 something 6 light years. So we could very easily fit our solar system. In fact, many solar systems fit in these nebula. Why do we need it that big? Well, those clouds are protective from disruptive cosmic radiation. So space isn't just space, it has all sorts of energy pinging around it, and they would disrupt the quietness one needs to form a star. And what does that quietness give us? The regions of that molecular hydrogen can collapse spontaneously if they meet a measurement of how dense that cloud is, called the Jeans mass. That collapse can be assisted, so cosmic radiation could help it. If it's random and disruptive, it will blow apart the star that wants to form. However, it can be assisted by any of these events here. But they call it when it affects a cloud or some sort of gaseous object, they call it a perturbation. And these external events can assist the collapse of that molecular hydrogen. Passing star, a nearby energetic event, a cloud collision, those type of things can push a little bit and help the Jeans mass start collapsing the star. When that star begins to collapse, a protostar begins to form. It's not yet a star because it's not yet. Anyone can help me there? What's it not doing yet that doesn't make it a star? It's not fusing any material, as in nuclear fusion. So what's going on in that protostar? It's a star heated by gravity collapse. So as the star begins to collapse, all that material is its own gravity, the density, the gravity resulting from that density reaching that Jeans mass ends up collapsing the star. It hasn't started nuclear fusion, as I said before, that protostar. Remember conservation of energy. So as it starts to collapse under the force of its own gravity, remember potential energy ends up getting converted to kinetic energy. All right, so you might have learned that in your physics in high school. Potential energy gets converted to kinetic energy. The kinetic energy, which ends up being the bulk motion of gas, increases. But kinetic energy, movement, also can be called something else. It's also called this stuff here, heat energy. Any movement random movement especially, results in an increase in enthalpy. The pressure also increases. And if the protostar is massive enough, eventually it gets hot enough from that collapse to start hydrogen fusion. and that hydrogen fusion, if it's big enough, can be sustained. Once it's sustained, several things happen. The collapse is halted, something called hydrostatic equilibrium is reached, and then once that hydrostatic equilibrium is reached, a new star can then be considered born. So what is that hydrostatic equilibrium thing? Well, this describes it very well, I think. Two opposing titans. So you're talking about the forces available to something you can feel the energy of 93 million miles away. So big energies happening, right? So it's two opposing titans fighting each other. So the pressure of the star, you can maybe see the core of the star here, and the fusion heat energy pushing out of the star, and you can see the gravity collapse energy pushing in on the star. So it's those two titan of forces that are keeping the star, those two fighting against each other, that's keeping the star stable. Why is it stable? Remember, a collapsing fluid heats and an expanding fluid cools. So as the star heats up and maybe expands a little, it cools. And once it cools, it starts collapsing again. So the heat, it's almost like breathing, right? It's heating up, expanding, and then it cools a little bit from that, and the pressure related to the fusion ends up, the temperature goes down a little bit, the fusion slows down a little bit, the star starts to collapse under the gravity again. So it's self-regulating in that way, and that's very good for us, because the star's been our star has been around for quite a long time, and for billions of years, and it has helped us for that period of time, and we want it to be nice and stable so we can be around for a lot longer. So again, the changes in the rate of fusion are opposed by the changes in the plasma expansion, and that is hydrostatic equilibrium. So how does this whole fusion thing work, that we understand the gravity part pretty easily by just being here on Earth, but how does this fusion thing work that's powering the star? All right, so I'm not going to spend a lot of time. Don't worry about the meaning necessarily of or the mathematics involved with all these charts, but here is sometimes it makes sense, right? So this fusion here shows the kinetic energy of a particle, the number of particles with the kinetic energy, and the white area shows the proportion of particles in the sample that do not have enough energy to create the fusion reaction. So everything on this side doesn't have enough energy. This blue area shows the proportion of the particles in the sample that have enough energy. So the blue portion here, on this side, those particles are moving fast enough to get into the two hydrogen can bang together and become helium. Or it actually takes 4 particles, but the 2 to begin one portion of the reaction, another portion to begin the other half, and then those 2 halves combine to get helium. However, there's a problem. In real life, they measured this blue portion, and they measured this white portion, and in order for those charged particles of hydrogen to bang together to form helium, to form the helium precursors and then the helium, it has to be way over here. So there is something else happening. It just wouldn't have gone. It just wouldn't have happened. The reaction just, too many. There weren't enough particles to sustain fusion in a star. So what else is going on? So it's a head scratcher in the sense that it's a little more weird science. It's quantum physics. This particular phenomenon is called quantum tunneling. The electrostatic repulsion of like-charged particles would dictate a much higher thermal energy for a particle collision to result in fusion that I just described. However, the smallest of matter is quite weird. They can behave like waves. The dual nature of light you've maybe heard of. It's both a particle and waves. Well, that doesn't only happen at light, it also happens on any quantum-sized particle. All those things can behave both like waves and particles. However, a physicist will tell you that's not really what's going on. It's a whole different phenomenon. But our first understanding, let's say it can happen both as either a particle or a wave. Small particles what is quantum tunneling then? This property that we are using from quantum physics. The small particles can change position without moving through space. They quote unquote teleport into the new nucleus. So it may be a little more accurate to describe it not as teleporting, because it's not like a wizard and I want to go over there and now I'm over there. It's more random in nature, and it's more like instead of the particle moving or teleporting, it's just traveling, it's just skipping through the next space over and going to instead of skipping from 1 to 2 to 3, it just went from 1 to 3 directly, and it didn't even see 2 or acknowledge 2. And that phenomenon called quantum tunneling. The higher kinetic energy has, the more likely it is to tunnel, and the quantum tunneling is required to make fusion go. So how does that quantum tunneling help us do? Well, what it does is it moves this line here, the required activation energy, back down in this direction to allow it to happen. So the tunneling energy, it actually will quantum tunnel into the collision, and now you have to meet this activation energy with the assistance of the quantum tunneling, and it moved this line back in this direction to allow the reaction to happen. What happens once the particle reaches there and it starts reacting? Well, E equals mc squared. You might have heard of that equation. What happens is 700 million metric tons of hydrogen is converted to helium per second by the sun. Well, how does that give us energy? The hydrogen turns to helium, so what? Well, what happens is that 5 million of metric tons of the matter that used to be helium disappears or gets converted to energy per second. So the energy of the hydrogen got that matter that disappeared or got turned to energy gets converted and powers the sun. And the equation that 5 million metric tons of matter goes directly into m here times the speed of light, and whoops, and now we can get the energy output of the sun. So seems relatively simple, but it's very complex, and we'll go into it a little bit more. The sun, remember this 5 million metric tons per second of matter going away and turning to energy sounds like a lot. Why haven't we run out of energy? Why haven't we run out of mass in the sun? Well, remember we talked about in the beginning there, almost 2 times 10 to the 27th metric tons is the total mass of the sun. So we're even at 5 million metric tons per matter, we're still not going to run out of material for another 5 billion years. We're all right. Oh, excuse me, 7 billion years. There's enough material to go on for about another 7 billion years. So we're okay, even though that seems like an insane amount of material. Now, I know you don't need to memorize this at all. I found it very interesting, but here is where we go take two of these, as I said, two hydrogen nuclei combine. They go to this intermediate phase. It happens again, so this thing happens twice, not to the same hydrogen, to another pair of hydrogen. It gives off a positron and some gamma radiation. They go through another step as it goes to this heavy deuterium proton. Once that happens, it ends up where these heavy helium, this deuterium, it goes into this 3 helium. The two 3 heliums, that intermediate combines, and we get our final helium, our alpha particle, plus 1 hydrogen. And here, this gamma, this gamma, this is a positive, and this is a neutrino. And so the neutrino goes off, the positron gets destroyed immediately, and the gamma radiation is where we're getting our energy from the sun. Larger stars, stars larger than our sun, go through this CNO cycle. So just a little arithmetic coming out of there. The atomic weight of normal hydrogen is 1.00747 grams per mole. Atomic weight of the normal helium molecule is 4.2602 grams per mole. And however, 4 times hydrogen is 4.0298 grams per mole. So you notice that there's a quantity missing. That quantity missing is these guys, the neutrinos, and the energy coming off from the sun. And remember that the mass is being converted to energy. And I just want to take one more quick description of what's happening there. People think when particles collide, say in a particle collider, that they fracture and they turn into pieces of what was there. And that's not what's actually happening when you look at these nuclear reactions. You have to think that everything is being converted to energy and then coming back into these particles. The particles are rearranging at a quantum level, and so it turns sort of like to energy and then back into particles again. So you need to, it's not pieces of atoms, it's not pieces of, it's a conversion to energy and back again. So it's a little bit different than what we think. That energy difference between the hydrogen and the helium, the 4 hydrogen and the 4 helium nuclei, that's what we are getting our energy from. Let's talk a little bit, now that we've talked about that fusion, we got the fusion behind us maybe a little bit. What do we know about stars and their sizes and their frequencies, and how do we know these things? What we can't know from maybe just looking up at a star. We can't know the size of stars or their luminosity from knowing their brightness. A sun could be, a star could be very bright and far away from us, or it could be dim and close to us, and they might look like the same brightness to us. Light's brightness, because it depends upon its distance from us. It has an inverse square relationship. Stars' brightnesses are classified by magnitude, and the star's luminosities, that's how much energy the star is giving off, can be classified by a unit of power like watts or absolute magnitude. We're using that unit magnitude twice. In this case, the absolute magnitude is significant because we fixed the distance at 10 parsecs, so we know that it should that all stars of different luminosities will be have different magnitudes at that standard 10 parsec distance. So what can we know from just observing the stars from Earth? Black bodies, stars are approximately black bodies, irradiate with color intensities with a predictable curve. Knowing that curve shape, the color index, we can predict the surface temperature of the star. And knowing the surface temperature, spectral type, and luminosity class, and knowing a whole lot of physics, we can know how much that star, the size of that star. And knowing the size of that star, the mass, it lets us know then many things about a star. So that's how scientists end up calculating. They need to measure the color of the star and the light coming off of the star. They need to go back to that spectrum, and here we are. We know that spectrum. We can see that spectrum. We can measure that spectrum. And then we plot it against the black body radiation curve. We'll just call it for that. And we'll look at this 6,000 one. That one seems interesting. This 5,000 K one. These are different temperatures. You see light bulbs now come in different Kelvin temperature ranges describing the light that's giving off. Well, it's referring to this black body radiation. And this 6,000 one looks very interesting because it peaks right here in this rainbow pattern, which looks a lot like this sun spectrum in its arrangement. And the reason is because our sun is about 6,000 degrees Kelvin on its surface, and this peak, that this black body radiation of an object that is 6,000 degrees Kelvin gives off this light. So it's not a coincidence. See Roy G. Biv, which is of course it's not a person, that's the mnemonic for measuring the color, the order of the colors in a rainbow or in a spectrum. So we will refer to Roy G. Biv for an explanation. Here are the various classes of a star. We don't have to go into the why these are labeled this way. The dominant lines, that's these lines here in the spectra. The dominant lines, these are the ions, the ions of the elements associated with those lines. This is the color of those stars, so it goes from blue at the hotter range to orange-red at the cooler range, and you can see those resulting temperatures. It's going again from hotter to cooler. So we know the colors of these stars, and we know their temperatures from that black body curve I showed you. So let's talk about some of these common stars you may have heard of. You've heard of Betelgeuse, Rigel, Polaris, Aldebaran maybe, Vega, Sirius, and the Sun. And these are their luminosities. That's the right at the Sun, how much energy it's giving off. The mass of the star, you can see it's decreasing here. The radius of the star, this one, something's going on there. It's a much bigger radius. And then the temperature of the surface. So why is this one a little bit different? It's, wow, that radius is big and it's relatively cool on the surface. Something's a little bit different about that Well, here's why. Because they took, and why it's a statistical phenomenon. Because you can see each of these is a point. Each of this color that might, as you're further away in the audience there, you might not appreciate it, but these are all points. These are all a single star plotted along this line. And we found that all stars of a certain age, called being on the main sequence, lie along this curve. This is the Hertzsprung-Russell diagram. This curve, the sun is about here, right about in the middle. The main sequence is where the star is still burning hydrogen, as we described in the fusion section. The sun is a G25 and is at not quite 6,000 Kelvin, 5,778 Kelvin. There are other luminosity classes, and wanted to talk here about Betelgeuse. Betelgeuse was different because it's not on this curve. It's moved off here into, it's not a giant or a bright giant. I believe it is a supergiant. So it's on one of these two curves along here. So it's no longer on the main sequence. It's no longer burning hydrogen, or at least primarily hydrogen. So it is along up here and no longer one of these stars here. This curve down here is white dwarfs. Those are stellar remnants. They have a temperature associated with them, so they're appearing on this diagram, but they are no longer burning fusion of any sort the way these other stars here are. So we talked about white dwarfs, so let's talk about what happens at the end of a star's life. Red giants and supergiants. When the sun uses up its hydrogen fuel, it will collapse until its core gets hot enough and begins to fuse helium to carbon and oxygen. So its successive cores build up inside of the sun, of a sun that's on its way out. Instead of burning the hydrogen primarily, it'll start burning the leftover or the helium that it had produced earlier, and will start burning, you start transforming that into fusing that to carbon and oxygen. That doesn't mean there isn't any hydrogen left, but that's on the outside, not in the core anymore. And so this shell of hydrogen, this shell of helium, and now shells of carbon and oxygen further inside begin to form. More massive stars will repeat that process that will happen to our sun. Where it stops depends upon its mass. So helium, hydrogen, helium, carbon, oxygen, neon, etc., are concentric active cores found in massive stars. Successive fusion types require hotter temperatures and therefore give off more energy. The sun or star will expand then to become a red giant or a red supergiant, depending upon what it's currently burning. Regardless of mass, fusion stops at iron. Iron fusion does not happen. Iron fusion is, instead of giving off energy, requires more energy than to fuse than it ends up giving off. So fusion stops at iron. Once fusion stops, the hydrostatic then equilibrium is gone. Those two titanic forces stop. Fusion's no longer pushing out. So what happens is gravity wins. The sun or star will continue to collapse until something stops it. What besides fusion stops a star from collapsing? In the case of a white dwarf, what's called electron degeneracy holds up the star, so that'll stop it. Particles with like quantum values may stay separate, the Pauli exclusion principle. The free electrons in such a star order themselves and provide a back pressure to resist gravity. So there's some quantum physics going on about the nature of the electrons, but also you can think, the charge of the electrons. But it's more two like charged particles will repel each other. Well, similarly, with different quantum numbers, these electrons can't occupy the same space, so the electrons repel each other from further collapse. It's not charge, it's not electrostatic forces, but it's quantum forces keeping those electrons apart from each other. If the electron degeneracy isn't sufficient at just under 1.5 solar masses, the stars will continue to collapse. So it's no longer a white dwarf. The star still has too much mass. It's still too heavy. So the next thing that happens is neutron degeneracy holds up neutron stars. Electron degeneracy holds up white dwarfs. Neutron degeneracy holds up neutron stars. Exactly like electron degeneracy, neutrons are excluded from occupying like states. Those quantum numbers can't be the same, so they start piling up on each other. Neutron stars get an additional assist from the strong force. The strong force is a weird force. We won't go into it, but it can push and pull. In this case, it's pushing out. Beyond those opposing forces, I've got nothing, and neither does the universe. So the star remnant will continue to collapse and form a black hole. That's how a black hole is formed. The star is too massive for neutron degeneracy to hold it up. It just continues collapsing. So here is examples of things that we can see from here in our telescopes, but also in astrophotography. This is the Ring Nebula, and this is the Crab Nebula. Inside the Ring Nebula is a white dwarf, and this is called a planetary nebula. Inside the Crab Nebula is a neutron star, and this is the remnant, a supernova remnant. So I'm not going to go into black holes. I hope to make that into a separate talk at some point. But I wanted to give you that end of the stars, and that is also the end of my presentation. So thank you very much for listening.
All right. Thank you so much, Paul. Thank you for everyone who joined us. So we are going to have a Q&A session. Once again, brief reminder of the safety rules for when we leave, because if I leave it till after question and answer, no one listens. Headlights on. We're not running people over. As tempting as it might be, those 10 points are not worth it. If you need to use the restroom, it's the porta potty in the back. We have a museum and gift shop open. After the presentation, I'll be in there and you can check things out. And I'm actually surprised it kind of cleared up. It's not as rainy as it was before. But and normally after the question and answer, we would be viewing things through the scopes. I don't think it's quite clear enough to take any of the scopes out, however. So, first question I'm going to do online. And after that, people who are here, if you have a question, hold your hand up and wave it about. And leave it up until I get to you, because otherwise I'll forget where you are. All right. So, our first question is, if you could hop in a time machine and go back to study the things like how the sun formed, would you?
I'm not sure that that's a very tough choice, right? Because who knows whether the trip back is even possible or not. Let's assume that it's a one-way trip. You would definitely be educating yourself possibly on that, but then you'd have to try to communicate back to people. And if you can't come back, then probably the information that you gathered can't come back. So I don't know whether it would necessarily be worth the trip. Plus, we are already gaining a lot of information by studying the rest of the universe. So why risk it?
All right. Any questions out here? Perfect.
Oh, okay. The elements that are not
need to hold it closer.
the elements that are not created in the core of the star, would they be lithium and beryllium and another?
It's the next lighter elements. I forget exactly which ones they
Yeah.
are, and I don't want to give you the wrong information. So I would say you have to look that one up. But really it's right in the periodic chart in the atomic weights. If you look them up in order, it's the next ones right after hydrogen and helium by atomic number.
I think you are right about at least lithium because that's as far as I could remember. I can count to 3. But that's neither here or there. The next online question was, how close could we get to our sun as humans with our current level of technology? I'm assuming this is like physically we hop in a spaceship and go, come on, let's go explore the neighborhood.
We have a satellite that is was just came into operation a year, 2 years ago. That it's making closer and closer approaches. I forget the name of the satellite, unfortunately, so I can't tell you exactly what it is. But we have a modern satellite made to do close approaches to the sun, and it is our maybe our nearest man-made object to the sun at this point.
But how close could a human get?
How close to
I think machinery can get a little closer than we can.
you start? I don't know but certainly the amount of radiation coming off of the sun is nothing to sneeze at. I don't know the how close we can actually get and survive at this point.
All right, question out here. All right, so our next online question is, if you could breathe the sun, would you be squeaky like if you inhaled the helium, or does hydrogen have a different effect on the voice?
I certainly different densities of gases will affect your voice in different ways. So there's probably some effect. I don't recommend breathing hydrogen, and certainly I don't recommend breathing plasma. So I would say the question's probably moot. If you're breathing plasma, I don't think you have to worry about what your voice sounds like.
This is true, but
It is an interesting hypothetical. I would say there would be an effect. Different densities of gases would have a different effect on your voice, definitely.
question. All right, so the next one is, what would your opinion of an electrical grid meltdown from solar flares here on Earth in our lifetime? What impact would it have on our lives? Like,
It's already happened. So the Carrington event is the first and major, most maybe famous. Happened in the late 18 or mid 1800s, and it happened to telegraph wires. Spurious electric currents came across, started fires at telegraph stations, caused wires to melt or break down at least, and it was a very large CME event. And I was just hearing from somebody who actually goes yesterday, attended a presentation from somebody who actually goes down to a member here, who actually goes down to Antarctica and helps measure these things to predict them. Of course, in the 1980s and other time, we've had blackouts that have been caused by solar activity. So it already has happened. We continue to try to, with technology, try to limit its effect, but it'll probably happen again in the future. I mean, the sun's an extremely powerful thing, and if it wants to mess with us, then we can just say thank you.
All right. So I have 3 more questions online. So I'm going to encourage our people online. If you have any more questions, do get those in. Do we have another question from our audience? All right. So the next online question is, speaking of sun activities, is UAC&J doing anything for the solar eclipse in 2023? And I believe this is referring to the solar eclipse that's going to mainly pass through Texas in North America on October 14th, which is a Saturday. That one's this year. I did actually look that up. We'll here at UAC&J will be in about the 25% visible, where we'll see about 25% of the occultation.
We do not have current plans to do anything for that. It would depend upon our ramping up our volunteerism to cover such an event. And since we're only in the 25% range, I don't think it's going to be something spectacular for us to view. But certainly, any type of event like that where we are within the in a range is certainly worth investing in some at least paper solar glasses, so you can look up in the sky and take a look. Those things are really neat to see. But the partials are not quite as spectacular as a total solar eclipse.
That being said, if we get enough people here interested in making an event for it, who knows what that might hold. We probably won't know for certain until much closer, since that is in October and that is several months away. Ken, do you have a question for Paul? No. Ken just gave me a panicked look. I put him on the spot. So, second to last question is, and I think it's referring to the slide you had on where you had the sun was converting hydrogen to helium. How many normal-sized balloons can you fill with that much helium?
Yeah. You can fill 1 million Earths inside to give you at least a ballpark in your a starting point, about 1 million Earths inside the sun. So however many balloons you can fit inside the Earth, multiply that by 1 million and you have your answer.
That's a lot of balloons.
That's a lot of balloons.
At least 3. Right. So our last online question is, how much research and how long did you need to research before you became comfortable giving a presentation on this topic? Because this is a lot of science and math.
It is a lot of science and math. Of course, I do have, as an engineer, I do have a background in the science and math, so I have a general level of comfort presenting it. However, I'm presenting to you more of a book report than something that I deal with on a professional level. So I'm presenting other people's expertise on these subjects. I did show the 2 gentlemen in the beginning of the 2 references in the beginning of my presentation, and I suggest for more and detailed and better understanding of the science, I gave an overview. I definitely recommend, if you want to gain a truer understanding of the science, pick up those references directly and get your better knowledge from those 2 gentlemen.
Yeah, and of course, like anything astronomy, stars are a very vast topic, and there's always people who super specialize. You're going to find people in the field who are like, I know all about, the surface and what the surface does with the injections and the coronas and whatnot. And then some people are going to be like, I'm really good at light. I can do all the light things. And then you're going to have me. I'm like, that's a star.
Well, in order, just so everyone remembers, here we are amateur astronomers, so we will run the gamut of people who are completely people. Kim just bought her first telescope recently, so I
I
did a big.
it was it's actually my second telescope,
Yes, your
but the
second.
first one I have bought.
Okay.
Because my first telescope I won for free at NEAF, before for like that was years ago. That was
that one was
that was
years
like
ago.
2018, 2019.
But you would say where would you classify yourself in your journey for amateur astronomy?
I'm only a baby.
So a little bit more less familiar with operating the telescope to people who have been doing it so long they can just point at random objects in the sky without really looking through the telescope. They can just look at it and immediately be on that object. To people here who are professional astronomers, and to people like I've referenced who are actually experts in the field. So we run the gamut, and it doesn't take huge chops in mathematics and science in order to enjoy amateur astronomy and to appreciate the history of science. If you can do that and want to see really cool stuff in the sky, amateur astronomy is for you.
Yeah. Plus, I still use post-its and cheat sheets. So no matter what you do, as long as you get out there, go look up your local club. Because we have people who come here from all over, all the time. We have people who come here from New York City, because we have some of the darkest skies available in New Jersey. So it really, your local club will be able to give you information on where the best places to look are around you, and then you can come to some place like us that have better skies. And with that, any last minute questions from our people here? Since there are no questions from our more questions from our online audience, I want to thank you all for coming out. Like I said, do check us out on our website, uacnj.org. I have my lovely constellation of social media here, and everyone have a good night.
Good night, everyone.